Hello, friends. Welcome to Science Talk. I am your host and resident oceanographer, Jasa. Okay, from a paper that will soon be published, it has been accepted for publication. It will appear in the Journal of Geophysical Research, Oceans. Changes in Arctic halocline waters along the East Siberian slope and in the Makarov Basin from 2007 to 2020. And a whole pile of authors involved with this. Cecilia Berosio is the lead author and PI. I want to go over the abstract, both and then the plain language abstract, and then I've got some figures, diagrams that I wish to go over with you that will hopefully uh, elucidate what's being said here. The evolution of halocline waters in the Makarov Basin and along the East Siberian continental slope, okay, saying the slope there, okay, East Siberian slope, not the shelf. So the slope is the portion that uh, is steeper, is examined by combining drifting platform observations, shipborne hydrographic data, go out there in a vessel and drop CTDs over the side, simulations from a global operational physical model from 2007 to 2020. From 2012 onwards, relatively shallow and cold Atlantic derived lower halocline waters previously restricted to the Lomonosov Ridge area progressed eastward along the East Siberian continental slope. Now, 2012 is an interesting year that when this started happening. Why is it? I'll tell you right up front. That was the year thus far where we've had the minimum ice extent, sea ice extent. Now, that was the year of the lowest sea ice extent and volume that we have records for thus far. Okay. Their eastward extent abruptly shifted from 155 degrees east to 170 degrees east longitude in early 2012, stabilized at 170 degrees east until the end of 2015, then gradually advanced to reach the western Chukchi Sea in 2017. Such eastward progression led to a strengthening of the associated boundary current and to the shedding of mesoscale eddies of cold Atlantic derived waters into the lower halocline of the Makarov Basin in September 2015 and near the East Siberian continental slope in November 2017. Mesoscale eddies are eddies that are typically tens, maybe a couple hundred kilometers in diameter. And mesoscale eddies are always pinching off the main current flow because of the fact that the Earth is a spheroid object that rotates. So you've got vorticity concerns, Coriolis concerns, and etc. And you're trying to balance all of that. Additional active mixing between upwelled Atlantic water and shelf water formed dense warm water supplying the Makarov Basin lower halocline. Okay, this is an important statement here. Okay. Active mixing between upwelled Atlantic water and shelf water formed dense warm water supplying the Makarov Basin lower halocline. Okay, you have the Atlantic water comes in, it's at a density that is greater than the surface waters in the Arctic Ocean. So it sinks in low and it gives off its heat and so on, but it actually starts to move upward. But also, Some of the older, they talked about earlier, cold Atlantic-derived lower halocline waters. Some of that gets upwelled. And I'll explain the difference later on, what's meant by the cold Atlantic-derived waters here. So we get that older water, kind of gave it away. So that colder water upwells, it mixes with the shelf water, forming dense warm water because of the temperature regime and of the fact that you're losing the sea ice, so it has a higher salinity content. And therefore, it helps affect what happens to the halocline. The increasing contribution from Atlantic-derived waters into the lower halocline along the East Siberian continental slope and Makarov Basin led to a weakening of the halocline, which is characteristic of a new Arctic Ocean regime that began in the early 2000s in the Eurasian Basin. Our results suggest that this new Arctic regime may now extend toward the Amerasian Basin. Okay, key points. Ice tether measurements in 08, 15, 17 in the Makarov Basin highlight changes in the upper and lower halocline properties. Cold Atlantic-derived lower halocline progressed eastward along the East Siberian slope, reaching the Chukchi borderland. The Makarov Basin lower halocline was increasingly supplied with warmer water resulting from the mixing of Atlantic water with shelf water. Warmer water. Plain language summary. In the Arctic Ocean, the halocline is a cold near-surface layer where salinity increases rapidly with depth. Right? More technical, general terms, a halocline is where we see a sharp change in salinity with depth. You can go up or down, but we see a sharp change with depth. This is important. The halocline isolates the sea ice at the surface from the heat stored in the underlying warm and salty water. Hence, the strength of the halocline is a key feature in the maintenance of the sea ice cover. Right there. Key feature to maintenance of the sea ice cover. The stronger the halocline, the more prevalent and more lasting will the sea ice be. You start weakening the halocline, it makes it easier for that underlying heat to diffuse upwards to melt the ice. In this study, we used various ocean measurements, computer models to document recent changes in the halocline in the East Amerasian sector of the Arctic. In this region, warm and salty water, usually found about 100 meters deep, was found to become closer to the surface from 2012 onwards. 100 meters deep. You may recall that in a video I did some time ago, where I've discussed Rebecca Woodgate's research, and she found that the halocline was shoaling, getting shallower, right, from about 100 meters to about 50 meters deep. We show that the shoaling of this warm water contributed to the progressive warming and weakening of the halocline in the East Amerasian Arctic Ocean. Warm water contributed to the progressive warming and weakening of the halocline in the East Amerasian Arctic Ocean. This weakening of the halocline is emblematic of the emergence of a new Arctic regime. New Arctic regime. Previously observed in the Eurasian sector of the Arctic, a region undergoing the growing influence from the Atlantic Ocean, i.e., Atlantification. Our studies suggest the regression of this new regime with shallow warm water and weakened halocline further into the Arctic. So, to kind of encapsulate in a couple of sentences the essence here, strong halocline reduces how much heat can diffuse upward to affect the ice. Halocline is weakening. That weakening halocline allows more heat to diffuse upwards, and that affects the sea ice. And you notice that 2012, the year of the minimal Arctic sea ice, this is when it all starts. So something happened right around that time that the halocline weakened, and we had all this heat moving upwards, melting the ice. And of course, it continues to flux into the atmosphere and continues to, later on in the year, prevent the ice from forming until later in the year. So the net result is that the open water season lasts longer. In fact, it's now been shown it lasts from about 5 months to now 7 months, i.e. more than half the year. Okay, that's the gist of it. Strong halocline, and it was deeper. Less heat can go to diffuse to the surface layers to affect the ice. Halocline is weakening. More heat goes to the surface, affects the ice. The halocline is weakening because of the warmer Atlantic water, the North Atlantic Intermediate water flowing in through Fram. The Atlantification of the Arctic Ocean weakens the halocline, affects the sea ice, basically contributing to it disappearing. Okay, let's take a look at some graphics to give an idea of what's going on here. I'll start with this one here. And this is looking down. Here's the pole, right? Okay, Greenland. There's Alaska, Chukchi Sea. All right. Here's all your shelf system here. They're talking about the slope, right, where it gets to this. Here's your very dark blue. So that's the bottom there. This is your slope. This is the shelf. The light blue is the shelf. The darker blue is the slope. That's what they're talking about. Moving all the way over to this way. And these little dots here are some of the surface flows here. So that's what they're talking about. They're talking about what's going on in this vicinity here. Okay. There's Lomonosov Ridge. You got the various basins here. Okay, so let me now pull up. We'll show you first what's going on in the surface. Here's the North Atlantic Intermediate water. Bring it in. There's your warm water there, right? So here's the Barents, Kara, Laptev, East Siberian Sea. So it comes in and goes in looking from above, looking down at the North Pole, in a counterclockwise flow. And as it's flowing, you notice that they indicate the cooling down of the water by the lighter shades of red, I guess, whatever that is, okay, as it cools down here. And then we have water coming in through the Bering. A lot of it worked its way through the Canadian archipelago. So we have water moving this way and this way. We then, as this water flows around, it creates what's called a transpolar current, which goes out through Fram and the Denmark Strait. So it's an outflow there. These lines represent riverine input. Okay. We have the Beaufort gyre here. That's looking down is a clockwise flow because it's a high pressure system here. This is a wind stress induced. Now you're going to look here and say, well, what's this motion here that is counterclockwise? Well, that's the remnants of the North Atlantic water coming in. As it gives off its heat, it cools down and it sinks. So this is and it's going to flow in this direction because of basically that was the direction already kind of predetermined. Right? It's still going to be affected, but it's going to flow in this direction here because you have Ekman pumping that pushes water down from the surface to depth, and then that creates an outflow. So it's almost like having, if you think of this in like atmospheric cells term, it's almost like having a low pressure system at depth. So then you're going to get a little rotational system that is in the opposite direction from what happens at the surface. So it's almost like you have two gyres kind of doing shearing motions to each other, but they're separated by, a couple hundreds of meters. That water that sinks, whatever, that's that cold derived Atlantic water they were referring to. So this gives you an idea of some of the, this is simplistic, but it gives you an idea of some of the surface currents that are taking place there in the Arctic Ocean. Okay. I like this one here. This is sort of like and you've seen me share this one with you before, but here's all that warm water moving in, a little split here, and it goes this way, right? And it goes this way, and you can see the what I just described earlier, the gyres at, I don't know if you can tell, but they're trying to show that this counterclockwise gyre is at a deeper location than the surface gyre here. But here's that Makarov Basin. Here's the Eurasian Basin, right? So here's the Lomonosov Ridge and the Canada Basin. This is that Makarov Basin that they were featuring in the paper here. And basically, the halocline is moving in this direction towards the Chukchi Sea. And this is the slope region right here. So this is where it's moving in. Here, once again, is the Pacific water inflow, diving right over to the Chukchi and Beaufort Seas, coming out this way, transpolar drift, again, riverine inputs, etc. And these little squiggly arrows, that's your heat flux. Either to melt the ice, keep the ice from forming, or eventually move into the atmosphere. So let's look at this one here. That's the North Pole. I kind of like that cute little graphic there. Shove a pole there. Okay. We refer to the Pacific halocline, which has a residence time of about 10 years. This very upper layer is called the polar mixed layer. This is what's under the influence of wind activity. So, and don't forget, when we look at some of these, for example, when we look at something like this here, the precise location of these movements here is going to be affected by the Arctic dipole, where the high and low pressure systems are located. For example, the transpolar drift could go blowing right out through the Fram, or in another configuration of the Arctic dipole, it aims this way and the northern end of Greenland blocks it. That will determine whether sea ice gets pushed out the Fram or stays within the Arctic basin. So here's the Atlantic halocline. Okay? So the Pacific halocline and the Atlantic halocline have a residence time of about 10 years. In other words, if you follow a parcel of water moving in, it will stay in this halocline for about 10 years before it's moved on, replaced, what have you. Here's the Atlantic water. This is the intermediate water. So the Atlantic water, which goes underneath the Pacific water and is above the deep water, which is really cold and dense. So when they talk about cold-derived Atlantic water, that's this Atlantic layer they're referring to. So this water moving in is warm at first, right? Water moving in through Fram. This is warm at first, and then it gives off its heat. It gets a little cooler, so it's going to sink. That's what they meant by the cold-derived Atlantic water. So you got this Atlantic layer. So as you can see, the residence time as you go towards the Fram Strait is less than over on the Pacific side. About 5 years different, 25 to 30 years, because because the water flow, the sphere drops are higher, so there's more movement. By the time it gets to over here, by the time it works its way around the Eurasian side, it slows down. So if it's slowing down, it's going to take longer to replace that water. And by the way, the word that we use in oceanography is called ventilation. To ventilate, do a turnover of the water basin, the water mass, whatever we call it, ventilation. So residence time, ventilation is kind of the same concept. And you can look here, you can see that we're talking a depth of about 900, 1,000 meters or so. And then it gets really deep in the Arctic Ocean. We're talking down to like 4,200 meters, right? So you've got the Atlantic layer, the upper 900 meters or so, and then down to 4,200 meters in like the Amundsen Basin, the Nansen Basin. Okay, here's the Lomonosov Ridge. Right here is the Makarov Basin that they're talking about. So you ventilate up over this way, you can flush out the water in the Canada Basin. But this is what they're talking about, moving the halocline around, and here we're having some communication. We're having communication with these different layers here, and it's affecting this halocline. And this halocline is going from basically 100 to about 50 meters. So that's what they're getting at here. You got the Norwegian Sea, Greenland Sea, deep water. So the residence time here on the Eurasian Basin, deep water, is about 75 years. The bottom water in the Eurasian Basin, the residence time or the ventilation time, is about 290 years. And when you get over to the Canada's Basin side, it's about 300 years. It's cold, dense water, sinks there, takes a lot to push that out. In other words, you have to have cold, dense water sinking, and as it interacts with this water, there's a little bit of friction that heats up the existing water down here, and it heats up a little bit, so it becomes a little warmer, a little less dense. It moves out and then gets replaced. So that's what they're getting at here. And this kind of shows you another aspect of it. Right? Familiar players here, right? Pacific halocline, polar mixed layer, Atlantic halocline, the Atlantic water, and then the Arctic deep water with the various basins, the Lomonosov Ridge. There's the Makarov Bridge basin there. This is the transect from which they did, that they used to create this little profile here. Okay, now what do we got going here? So we have pressure in decibars. So you split this graph into two locations, kind of this way here. So on this side we have potential temperature. On this side we have salinity. Let's look at the potential temperature. So they're measuring temperature. CB is the Canada Basin. MB is the Makarov Basin. AB is the Amundsen Basin, and NB is the Nansen Basin. And when we look at the temperatures, we can see, and looking at the pressure, that within these basins, we can see there's some vertical mixing going on here. And then we see what? We see basically, since this temperature, a thermocline, and then coming down to the temperatures that we see here. So, and the temperatures, which is really interesting, shows it to be, about 0 to 0.5 C. That's potential temperature. has not yet been corrected to what we call the in situ or theta temperature. So potential temperature has yet to be corrected. The salinity is interesting, and as you can see here, they indicated the halocline. Because if you look over here, salinity is pretty, we have a basically almost uniform layer here, and then it does what? It starts to increase, and then it settles down to about 35 PSUs, practical salinity units. So what they're getting at in all of this, and now we can go back and look at the abstract again. The evolution of halocline waters in the Makarov Basin and along the East Siberian continental slope from 2012 onwards, right? It is progressing eastward along the East Siberian continental slope, moving a whole 15 degrees longitude, stabilize around 170 east, and then gradually advances to reach the western Chukchi. Such eastward progression led to a strengthening of the associated boundary current. Let me just pull that up for you. This is the boundary current that they're referring to. So it's moving about. And as I stated before, the really significant aspect of all of this is that the halocline in the past served as a deterrent for heat flux to go to the surface and therefore affecting the ice. Well, the halocline is weakening. It's getting shallower as well. That allows more heat to readily diffuse to the surface to melt the ice earlier, prevent the ice from forming later in the year, and obviously some of that's fluxes to the atmosphere. And it's all part of the Atlantification. And starting in 2012, the year of the minimal sea ice. Weakening halocline allows for more heat to melt the ice. And we now have a longer open water season. All part, and I've discussed with you in some really lengthy prior videos some of the mechanism, looking at the Barents and the Carasees and etc. And I showed I showed you the progression, the evolution of the effect of the North Atlantic Intermediate water moving through the basin, moving through the Arctic Ocean on the shelf process as well. This is further evidence that there's a new Arctic emerging, a new regime coming through. Part of the Atlantification, part all tied in with the weakening halocline, allowing more heat. And we'll just have to see where it goes from here on out. I remember one of my prior videos, someone made a comment asking me about, what's going on in the Arctic Ocean. And I said, for a small body of water, it is surprisingly complicated. It is. And I remember stating in that post that, in my assessment, the key to understanding what goes on in the Arctic Ocean is the halocline. This study would seem to support my contention on that score. So I hope I didn't confuse the crap out of you guys here with this one, but this is going on. Strong halocline, reduces heat flux to the surface. Weakened halocline getting shallower, more heat fluxing to the surface. Affects the ice, affects the atmosphere. along with the Atlantification that's going on. New Arctic regime. Stay tuned. Thank you for your time.